Hello and welcome to this Simulator Spotlight presentation. My name is Jason Tranter, and in this presentation we're going to look at iTeachResonance. And as you can guess from the name, it's all to do with understanding resonance and natural frequencies and mass and stiffness and damping and all those sorts of things. To start with, the simulator can start in this very basic mode, and by clicking on this button I'm telling it, well, it's fixed at this end, sort of like a dieting board in a way. It's free at this end, so it's cantilevered, and I can excite it with different vibrations. But if I just click on the little number 1 there, it's the first bending mode, so that's we get to see what it looks like in first bending mode and second bending mode and third bending mode. And we can go to a clamped situation, and let's do third bending mode in that case. So now it's pinned at this end, fixed, and it's fixed at that end. There's our third bending mode, which you can look at a wireframe drawing or the solid one. And we can also model a string and say, what does the second bending mode look like if it was a string, like a guitar string or something like that. Anyway, we can do all of that, but there's a whole lot more if we go into the detailed mode. Now we reveal all the options, and there are so many things we can do with this simulator. It's unbelievable. You could run a whole course on this simulator, to be honest. And I want to stress that with all the simulators, including this one, it's all real. We are calculating this, we're modeling it properly, we're calculating it. It's not faked and rigged. It's all really real. You can change values and it responds the way you should expect. So I'm just going to change a couple of settings here so we see all the mode shapes and cantilever. So as you can see, it's now pinned here and it's vibrating just because of what I was doing a moment ago. Right here I can change the vibration that is exciting the structure, and this is a picture of the spectrum, if you like, that it is generating. As I increase the frequency, it starts to respond based on the vibration that I'm generating. Imagine putting a little motor on this structure that could generate a single vibration at a single frequency, and that's what we're doing. And we're seeing, well, how does it respond? But if I increase the frequency and I happen to get right on the natural frequency, and that's what these red dots actually mean, then there's our first bending mode. And if I increase the frequency and I go up, at some point you can see it sort of bouncing up and down, which is first bending mode, and also starting to get that twist in it, which is second bending mode. So if I go up higher and get closer to second bending mode, now you can see that dominates. I'm just going to make that a smaller motion. So that shows me the single frequency, or the vibration I'm using to excite it. Here is my Bodhi plot. I can see the first natural frequency, second, third, or the first bending mode, second bending mode, third bending mode. This shows the phase change, and you can see that as I change it, you can see the response. That's the input excitation, and it gets amplified according to where it is along this graph. So first bending mode, right on it there, and second bending mode, there's actually a bit of both there, and we get into where second bending mode dominates and where third bending mode dominates. But for example, we can get a little bit tricky, and we can say, what if we got more complex vibration, and I've got a 1x, a 2x, and a 6x. I'll just bring that out a bit. 1x, 2x, and 6x vibration. Well, as you can see here, my 1x corresponds with the first bending mode, 2x will excite it a little bit, and the 6x happens to be exciting my second bending mode, which I can see here as well. First bending mode is being excited by my 1x vibration in this case, but 6x is exciting my second bending mode. And you can see how much movement there is. I'll just dampen that movement down, just stop as much amplification of the movement so we can see it. But you can see it, we've got the movement up and down, which is first bending mode, superimposed with the second bending mode because of the nature of the vibration that's exciting the structure. And look, goodness, we can do so many things. We can excite it with different sorts of vibration and all kinds of things, but we can't spend too much time on all of that right now. We can change the dimensions of the structure, sort of make it thicker and see what effect that would have on the structure. We can I'll say that was wider, and we can make it thicker down here. Oops, a daisy. We click there, and now you can see we've just changed the dimensions. You can see the thickness down here. But let's change the source of vibration. You can see now I can only see the first bending mode and second bending mode on the graph. Scale there. Anyway, we'll just click that to a bit of a cheat to make it go. So there you can see it down the bottom. It's thicker and it's wider than before. We can also artificially change it. Look, all I can tell you is there's lots and lots of things we can do with this simulator. We can see the polar plot as well. Let me just bring that back so everything's nicely on the screen there. Okay, so now we've got all three modes on our graph. I can look at a waterfall plot and I can fully simulate the entire run up, run down process. You see all the natural frequencies being excited. We see how the structure animates and all sorts of things. We can see a Campbell diagram. We can see what would happen if we did peak hold averaging during a run up, run down test. We can even do ODS tests. We can say, let's record the vibration and see what the vibration's like. Now what we might want to do is just make the vibration a bit more interesting. So let's get it moving a little bit, just a bit more interesting, as I say. We'll go to the ODS test and we'll record the vibration. So it's kind of like having vibration sensors at all these locations, and we see what it records. You know, one of them's just seeing an up and down movement, one's seeing a bit more of a, you know, two frequency movements and so on. And then what we can do is say, okay, let's stop that animation, and then wherever I move the cursor, we make it move according to, it's like playing it in time. So as I move the cursor across, we see exactly how it responded. It's like a time-based ODS. And we can do that as a frequency-based ODS as well. There's the peak for the first bending mode, there's the peak for the second bending mode. We can even do modal analysis and say, what if we struck it there? And oh goodness, there's so many things we can do. We can see exactly what the frequency response function would look like, and coherence and all sorts of things. So you can imagine that a simulator like this we use at different times to show the real basics, and slowly, depending on where we are in the course and which course we're in, we can reveal more and more functions so that we can really understand the nature of mass stiffness and damping and so on, and really understand all of the testing methods. Anyway, I could spend another hour on this simulator, but I think we should probably just say that's a good enough demonstration so you see what it's like. I hope you enjoyed that presentation, and thanks very much for spending the time to view the presentation.